Hey everybody, in this video we're going to take the graph of f and we're going to use the picture, the actual curve, to discuss what we can tell about the derivative. This is going to be very useful for us as the derivative can actually tell us about the original function. So we're actually going to look at it from function to derivative today, but eventually you're going to use the derivative to help you inform you about what the original function would have looked like. So graphing the derivative. When graphing a derivative by estimating the graph of f of x, look for the following characteristics. So here we have a blue curve f. Number one, where the slope of f is positive, negative, or zero. Those are the things you're going to look for. They help you learn about your derivatives function, its graph. Number two, where the slope itself is increasing or decreasing. And these are all the things we're going to discuss on this picture here. Now, this picture is got a lot going on. So let's just start with number one. And in number one, I want to start with talking about where the slope of f is 0. All right, why are we talking about the slope of f? Remember, the slope of your function, slope of f, is the same thing as talking about the slope of the tangent line. These are the same idea. So, if the slope of our function, or the slope of the tangent line, is, for example, 0, what does that mean about our function? Well, if the tangent line is 0, that means, remember, this is slope, so that means the rise is 0, but the run is a number. So we're in a situation where we have a horizontal tangent line. Remember, slope is 0 means horizontal tangent line. Now I want you to look at this picture, and I want you to look for where there's horizontal tangent lines. So typically, the horizontal tangent lines are going to be at what we call the peaks and at the valleys of our function. Okay. You'll also find occasionally a horizontal tangent line in between, so it kind of flattens out, but then it continues up again. This is going to be one that might trick you when we start graphing, so we're going to learn how to watch out for those. Over here, you might think, oh, this should be a horizontal tangent line, but it's not. Why is that one not a horizontal tangent line? Well, this is a cusp. So when you're talking about derivatives, cusps are a problem, and here I'm going to explain why. If you take a point, like this point right here, the point where we want to know the derivative at, and you pick another point. So here's your secant line, roughly. Now remember, if we take the secant lines and let the secant lines approach the tangent line, what's happening here? Well, we're approaching this vertical line right here. If we go the other direction, we take this secant line and we let it approach the tangent line. What is it approaching? It's approaching the vertical tangent line. So remember, when you have a vertical line, the slope of a vertical is undefined. Okay, so watch out for those. So you might think it's 0 because it's at a peak, but because it's a cusp is going to be an undefined slope because it's going to be a vertical line, vertical tangent line, therefore it's going to be undefined slope. All right, so we talked about 0. We pointed out that this one is not a 0. What else do we talk about? We can talk about where the slope of f is positive. All right, remember, slope of f is really just talking about the tangent line slope. So what do we know about slope? If the slope of a tangent line, or any slope in general, is positive, what does that mean about our curve? Well, what kind of line has a positive slope? That would be a line like this. Remember, you always read from left to right. This line has a positive slope, whereas this line has a negative slope. So if your slope is positive, that means your curve is increasing. So for example, right here, if I pick this point and I draw a tangent line, this tangent line has a positive slope. So your curve is increasing. All right. Over here, though, if I draw a point and a tangent line, so remember your tangent line follows the curve, only touches at that point. Here we have a negative slope. So our derivative is negative because our slope is negative, and its negative slope means our curve is decreasing. We're always read left to right. And if we continue on over here, we can pick a point and we have a positive tangent line slope. So our curve is increasing. Continue on. Here we still are increasing, so our slope has a positive value for the tangent line. And then finally this section here, we draw a tangent line and we have a negative slope. So our curve is decreasing. Okay, so where the slope is positive, we're original function is increasing, or the slope of the derivative is negative, or where the derivative value is negative, the slope of the function is negative. Let me start that over. When the slope of f is positive, the derivative is positive, your function is increasing. When your slope is negative, your derivative is negative, so the function is decreasing. All right, the last one here, we could talk about whether the slope itself is increasing or decreasing. So we talk about the curve increasing, but let me show you. This curve right here is increasing, okay? But at every single point, we have the same slope. Along this curve that we're talking about here, we don't have the same slope at every point. The curve is increasing. Let me clear this out so we can look at it. But it's increasing at different rates. So let me show you. If I take this slope right here, this tangent line, versus the one here, this tangent line. What do you notice about the tangent lines? The slope is getting bigger as we go along the curve. So the derivative is increasing. The value of the derivative, the value of the slope is increasing. If we go down this next section, look at the tangent lines. Look at the slope of the tangent lines. What are they doing? The value of these slopes is negative, but the negative values are becoming closer and closer to 0 as we go down this curve. So these negative numbers, be careful, this is a little tricky. So for example, if this was a negative, it's a good slope, negative 1/2, this would be a negative 1/3, a negative 1/4. They're getting smaller in terms of the value, but they're negative, so because they're negative, they're actually increasing. So the derivative is actually increasing. The curve is decreasing, but the slope values are increasing. I know it's a lot to take in, it's a lot to understand. So you have to pick something that you know. My suggestion is start with the zeros. Where the derivative is 0 is at the peaks and at the valleys. Mark those first. Then look in between those. Is it increasing? Then your derivative is positive. If it's decreasing, your derivative is negative. If the slope values are increasing or decreasing, that's going to be even more useful when we get to the second derivative discussion. So we'll talk more about it then. All right, let me show you an example of what you might see. Like I said, this is a graph with a lot of information. All right, so here's a little bit more reasonable graph. So what I want you to start off with is where the tangent line has a slope of 0. So look at this graph. Remember, slope of the tangent line will be 0 at the peaks and at the valleys typically. So let's find the peaks. So here we have a peak, and here we have a peak. So at these points, the derivative, the slope of the tangent line, is 0. Also at the valleys, so somewhere around here and here, the derivative is equal to 0, because these would have horizontal tangent lines. All right, let's start with that. So our first point that we're interested in, remember this is f here that we're looking at, is at x is roughly, we'll just call it -2, and the derivative value is 0. So this point here is for the derivative, okay? So at x is approximately -2, the derivative is 0. If I want to graph that, I would go over to my derivative graph and I would plot it. X is -2, 1, 2, and the derivative is 0. So we put a point at 0. Let's go to the next point. So next point, x is 0, and the derivative is 0. So we go put a point at 0, 0 for the derivatives graph. Then at x is 2, our derivative is, again, 0. So we go to +2, and we put a 0. And finally at, let's see, 3.5, our derivative is 0, and we put a point there. So 1, 2, 3, 4, so 3.5 is right about there. All right, so those are a good starting point. I like to start with the zeros, and then in between, you just need to fill it in. So let's start with all the way on the left and talk about this piece right here. What do we know about the slope of the tangent line along this piece of the curve? Well, let me draw one. So if I draw a point and a tangent line, roughly, very roughly, slope and tangent line, what do all of these tangent lines, it's kind of vertical, sorry, should be slanted. What do all these tangent lines have in common? What's happening on this piece of the graph? Well, the curve is increasing from left to right. The curve goes up. So that means that your slopes have to be positive, which means your derivative has to be positive. Well, what does that mean when we go to graph the derivative? Well, think about this as being the y value on your y-axis. To the left of our first 0, over here on the left, what does our derivative have to be doing? Our derivative has to have positive values, which means our curve has to be up above the x-axis, coming in to this point, -2. Okay. Let's look at the next piece. So, let's see what, I'll use my rainbow color. So this section right here, what do we know about the derivative? Well, pick a point and draw a tangent line. What do you observe about each and every tangent line along this piece of the curve? Well, the curve itself is decreasing, so every single point is going to have a negative slope. So in this section, the derivative is going to be negative. So our curve came into at 0, it crosses the 0, and it has to go negative in value, so we go down. Eventually, though, we have to get back to our next 0. How low we go, that's not important right now. This is called a sketch. It's not perfect graph, it's a sketch. I'm getting an idea of what's happening. So that would be the next one. And then over here, what's happening to our function? Our function is again increasing, which means our derivative has to be positive. So we're going to cross our 0 and go up and be positive, and then we're going to come back to the next 0. And on our picture, we're going to analyze what's happening between the next zeros. Again, our curve is going down, so again, we're decreasing, the derivative is negative. So we go below the x-axis to say that our derivative has negative values. How low? I have no idea. I don't care right now. We can make that more specific later. And then we go back to our 0. And the last section right here, our function is increasing, so our derivative has to be positive because there's positive slope at each tangent line. So we're going to cross the x-axis and go up and be positive derivative values. All right, so that is a rough sketch of what the derivative would look like here. Hopefully that gives you an idea of what you're going to be looking at. Most of your problems will involve you clicking the right one, so multiple choice, so that's huge help to you, I'm sure. But it's good practice to do them from scratch as well. So key points, if you had the original function, look for the peaks and valleys. That's where your derivative is 0. Start there. Then, if it's increasing in between, you have a positive derivative value. If its original curve is decreasing, you have a negative derivative value. All right, one more thing I want to talk about. Differentiability implies continuity. If you are differentiable along your curve at a point, then f has to be continuous. There's actually a really cool proof of this theorem in the book, so if you have time, go check it out. But basically, the limit definition of a derivative, if you break it down, you're able to show, using that limit definition, that if the limit of the difference quotient exists, then you have to also have that the function exists, that the limit exists at the point, meaning the requirements of continuity are satisfied, but also that those are also the same. The limit at c is equal to the function at c. So it's a cool theorem to go check out the proof if you have time. You can check it out in the textbook. And that's all I have for you right now. Remember, study hard, and I'll see you in the next video.